There are other tools such as see this Verilog A, which I mentioned earlier. See, that is an extension to Verilog to also handle analog. But I don't believe there is any public domain tool which can use Verilog A. So unfortunately, we will not be able to do any exercises on Verilog A. Having said that, it is very common to see people in the industry make use of both Spice, Verilog, and even MATLAB. So MATLAB is also a very important tool that you should know, right? Um, so not only MATLAB, but also there are some public domain versions like I think Octave is one of those softwares which is available, right? So MATLAB also comes with Simulink. I don't think Octave has anything like Simulink, but in the industry, you will see a lot of people use these tools. Okay, Simulink, MATLAB, or Octave. So these are also very useful in modeling systems, right? So I assume that many of you have access to MATLAB. So I will encourage you to use MATLAB and Simulink. I don't have access to Simulink here, but if you have, I'm sure your college will have. So you need to use Simulink that helps you to simulate slightly bigger systems. Okay. Similarly, MATLAB. Okay, if you are trying to design an analog filter or something of that nature, or something that has both digital and analog components. Such things are easily done in MATLAB. So that is something that I just wanted to mention to all of you, right? How many of you have used MATLAB? Let's see. How many of you have used? You can raise your hand or something. I don't know. Where is chat? I don't know. I mean, I couldn't see the responses. So I'm assuming that many people said that they have used. Is there anybody who never used MATLAB? Good. So please, it is something that is used a lot, right? So you should use MATLAB and also maybe Simulink. Both of them are important tools, right? So what can be done in the absence of, let us say, um, an actual simulation tool, right? So we can try to write maybe a class or something like that. See, that is the next best thing that we can do, right? So let me ask you guys, right? I want to develop a model for a, let us say, an analog to digital converter, right? So let us say there are many types of analog to digital converter, right? One of them is the, let us say, the SAR converter, right? SAR stands for Successive Approximation Register. Um, so I'm sure you know how it works. Can anybody sort of explain how it works, how the SAR ADC works. I'm not sure how many of you are in second year, third year, etc. So I don't know. Can you, because some of you may not have studied also. So is there anybody who has never studied as SAR ADC? So you can chat, you can put as comment. Is there anybody who has not studied it? So Dhruang Patel says it uses comparison and gives, yeah, right. So what is the input to such a module? Suppose, let us say I want to build either a module or a class. Let us say class ADC. What are some data that we can represent inside the class? And what are some functions that we can represent? What are some functions, tasks? What is inside a class SAR ADC? Let me compare it here. Okay. So if you want to talk about an A to D converter, the input is an analog signal, and we have to. So we can't really handle an analog signal, right? So we have to take, sample and hold, right? So we will make samples, and we'll assume that the value remains, you know, at this level, right? So if it's a sinusoidal signal, so we'll have to take samples. There is a circuit that takes samples and holds those samples when the conversion is happening. Right? So we have values coming in which can be in some range. So let us assume that the maximum value I get is plus 5 volts, and the minimum value I can get is minus 5. So the analog values or in minus V to plus V. And we are going to divide that range into certain number of divisions. That is the resolution. Okay. Suppose I am looking at uh, 256 resolutions. That means I'll divide this up into 256 parts. So from minus 5 to plus 5, so there is actually 10 volts range. And I can divide them into 10 by 256 volts. What that means is I recognize 0 volts. I recognize 1 by 256 of a volt. I'm sorry, 10 by 256 of a volt. Then I recognize 20 by 256 of a volt, and so on. Gas will be, I suppose, 128 by 256 of the volt. Right. And in the other way also. So I recognize minus 10 by 256, minus 20 by 256, etc. And the last one will be minus 128 by 256 or minus 5 volts. So if the voltage is in between the two, so we'll have to sort of either use this one or this one. So if this, you can use any heuristic. Okay. So that is what the sample and hold would possibly do, right? It will make sure that we don't get anything in between. We'll use, we don't have to resolve between these two. And then our binary code, right? So we have, let us say 8 bits. We have 256 levels. So we can have up to 8 bits. So we could assign maybe 0 to 0. So this pattern could be assigned to 0. And positive numbers can be assigned to this, and negative numbers can be assigned to this. So the largest positive number I can have is 0 followed by 1, 1, 1. So that will represent perhaps 127 by 256. And similarly, I can have minus 128 by 256 multiplied by 10. Okay. So we'll have to have a way to check what is the level. And depending on that level, we can assign the appropriate code. So one way to do that would be, maybe we can start with a register which is loaded with, let us say, 0. So we have a register which is loaded with 0. And when I get an analog value, let us say 5 by Let us say it is 5 by 256th of a millivolt. 550 by 256 volts is what I get. So we will use some sort of a digital to analog converter. So inside the ADC, there is a DAC. Okay, this will convert this value to an analog value. In this case, it will say 0. Then we can use an analog comparator, which will compare these two values. And if the value here is lower than this, then we will increment this register, because you know this represents 0, and we are seeing that there is a positive value, so we will go to increment. And the comparator will again compare, and this will happen till this becomes, let us say, the value 5 comes here. At that time, the DAC will convert this to, let us say, 5 by 256 of a multiplied by 10 millivolts or volts, and then the comparator will give a 0 or something. Then we know that it has matched and we stop, and that is the final code. So the register can be incremented or decremented. Okay, suppose I give a negative value, okay, then I may have to decrement the register. So we'll assume that when we reset this system, the register is set to 0, and then depending on the value, if it is a positive value, we keep incrementing the register. If it is a negative value, we keep decrementing the register. At some stage, a match is expected to happen. Is it clear how it works? Any chat? Op amp register buffer. So you can see that there are some digital components also. Okay, we need a register, we need an incrementer, decrementer, right? Then we need analog components like DAC and comparator. So that is the reason why it is called as a mixed signal circuit. Okay, it uses both digital and analog. In addition to that, I think nowadays they integrate a lot of other things, right? They may even have some password protection, so many things like that, right? So most of those are digital, right? So how do we model this guy? So any ideas on how to go ahead and model this? What would be the function new here? What do you think I should specify? Suppose I were to bring, suppose I were to write a test bench. How can I create a sample ADC or example ADC? What should I give here? The ADC is defined by what? Of course, we can keep a register. Okay. So maybe we can keep the accuracy or resolution is also something that we may have to give. Maybe we can say I want 8-bit ADC. So that the ADC should be able to use that information to create an 8-bit register. Similarly, I should be able to say the maximum value is 5 volts and the minimum value is minus 5 volts. That is the range. So how do you think I can use these things here? So we should possibly write, a num bits, real max value and the real min value. If I want to be ambitious and create a SAR register, the register that I talked about, that is called a successive approximation register because it approximates the input value successively. That is, one after the other. It cannot do it right away. It may take some clock cycles for it to do. It will take maybe in the worst case, it may take, I think it may, see, suppose we have guessed the value as minus 256, I'm sorry, minus 5 by 10 into 256, and the actual value is, so it may take many, many clock cycles for it to finally reach. So, see, some people have tried to improve these things. Okay. You don't have to go one step at a time. You can try to jump and come back. So there are some variations. You don't have to go linear search. You can do maybe binary search. So many such variations are there. But we are going to keep it simple. We are going to assume that it's going to just increment or decrement. The guess is always zero. We assume that the input voltage is zero, and we're always so how do I create the register whose bits is num bits? See, if you do something like this, right, you have to give the maximum. Okay. See, that is one way. You could say that, the maximum value here I'm going to take is maybe I can go up to 16 or something like that. So this is a successive approximation register. And if somebody says 8-bit, then I will only use the last 8 bits. Or you will have to declare it as a SAR like this. You will have to declare it as a dynamic array. Okay, that may make it pretty complicated. So maybe we can use the previous method. We can assume that nobody will ever want to do more than 16. So I'm sorry, 15 to you. This is the maximum length ADC will be 60. So we can store the length. int number. So that we can say this dot numbers equals numbers. So we can store. So now the ADC knows that it is a 8-bit ADC or whatever it is. We can also store these max and min values. So real max and min. So that also it will show. This dot max equals max. This dot min equals. So here I have assumed it is 5.0 and minus 5.0. And maybe we can increment, we can set the register to 0. So SAR, let us say 0. We make it 0. And of course, we can build a task called display. That is the easiest thing to do. We can print the value of the SAR. So we'll print it in both binary and decimal. And we can possibly accept a level. We can say int, no, mode. So normally, if you say if mode equal to 0 or something like that, then we'll only display SAR. But if somebody gives else mode equals 1 or something like that, they can give more details. Numbits equals max equals min equals then SAR equals. So display takes a an integer and we can customize what is displayed. Okay, if you want more detailed information, you can say ADC, say example ADC dot display one. Then we can also try example ADC dot display 0. So right now it doesn't do anything. It just initiates itself and it displays some information. It doesn't do anything great. If I'm going to say this way. The Icarus may be able to do this. So we declare example ADC as a object of class ADC, and then we allocate storage here, all the constructor function. Then we display. So right now, what is the reason? What is the reason?
Statement.
Huh? What is the reason why it didn't store this value? Hmm. Okay, so like I'm surprised. Hmm. Okay. Sorry about this. I thought. Hmm. All right, we'll go ahead and develop it in Cadence only. So what is the next thing? Okay, we may have to declare a task called convert, right? And it takes a real value, which is value. So value is an analog value. So we have to convert this SAR value using a DAC. Okay, so maybe we can create a DAC function. So instead of saying bit 15 to 0, perhaps we could design time bit 15 to 0 is sort type. So that at least we don't have to do it everywhere. Or we could make it a function also. So a DAC is a function which takes as input this R value and returns the analog value. So the analog value has to be a real value. So help me write the DAC function. When it is, so we have to take the What is the logic for DAC? See, if this R value contains see, suppose I have, let us take a very simple example of a 4-bit register. So we have 0001, 0010, and so on up to 01. And on the negative side, we have negative numbers. So that will be 1111 is -1, 1110 is -2, and so on. The last will be 100. So this should correspond to plus 5 volts. This should correspond to -5 volts. And this should correspond to 0 volts. And there are 16 levels. So this should correspond to 5 by 16 of volts. So 10 by 16. This should correspond to 20 by 16. So, and similarly, this should correspond to minus 10 by 16. So how do I convert? What is the equation that I should use? I should treat this R as a signed number, right? So in this case, I'll get 0. So here I get 0. Here I get -1, -2, etc. And I get -8. And here I get 1, 7. So I need an equation that converts this number to this. I will give you the min and max. So tell me, anybody has an idea? So 10 by 16 is always going to be there, right? It will be multiplied by something. Okay. So so 10 by 16 multiplied by that the value star. Will that not work? If star has the value 0, you will get 0. If star has the value 1, we'll get 10 by 16 into 1, and so on. For this guy, unfortunately, we'll get 7 by 16 into 10. We'll never be able to get exactly 5 volts. We'll be a little bit. So the DAC is straightforward. So I believe we have to declare SAR as a type signed. So the conversion should be take the value in SAR and convert it into a real number, multiplied with the max minus min divided by 2 to the power numbers. Maybe we can put real. This is what it should return. Okay. So we can verify that here. We can keep a int I, and for I equals 0, let's say I equals minus, in this example we are doing 8 bits. Okay. So minus 2 to the power 7 to 2 to the power 7. What to do is dollar display percentage 0 DI, and then the converted value is percentage. So I will be printed here, and example abc dot convert. No, wait. We are only converting the SAR value. Okay, this is not a real value. This is a R type. So the converter takes the SAR digit, the register SAR as input, and it returns the corresponding value. I hope I did this right. Let us convert and make sure it works. So when the value is minus 128, we get minus 5 volts, and so on. And when we get to 0, we get 0 volts, and so on. Okay. So finally, we will get 4.96. We will not be able to get 5 volts. So this is just a test for the converter. So the convert function we have tested. This is only that. Only that. I made a mistake. This should have been called that. Now, what is the actual convert function which takes the analog value? So the convert function takes a analog value and returns a SAR type. So it should go through that algorithm. Okay. So it should check if the value is very close to the value will never match. Okay. The value may never match the actual value. So it should be compared with, so we'll compare the DAT value of the SAR. If it is less than value. So if this is true, then we decrement SAR. Otherwise, we increment SAR. And we keep doing this till, so we have to put a while loop of some kind. So while forever loop, which is better. See, unfortunately, I can't write while is equal. I can't do that. So let us try forever. If uh, that of SAR is less than value, then we have to increment SAR. Else, if that of SAR is greater than value, then we should be careful. We should subtract the two error. We should write error, real error. We have to be careful. No? Error equals the difference between the value and the SAR, DAC of SAR minus value. And if you want, we can even take the absolute value. I don't know whether there is an absolute value available, but it's not difficult for us to write our own. So absolute value of x is defined as x if x is greater than 0, then it is x itself, otherwise it is minus x. So we can define a small function called abs, which is defined as if x is greater than 0, then we'll return x itself, otherwise we return minus x. We can possibly use that function here and get the absolute value. If this error is within some tolerable limit, okay, if it is less than, let us say that that 1 bit accuracy, 1 bit accuracy happens to be 1 by 256 times. Okay, so accuracy is 1 by 2 to the power num bits times max minus min. See, this is the maximum we can, I'm sorry, this is the minimum step that we require. If the error is less than or equal to accuracy, maybe we can stop. We are done. Otherwise, we depending on if the error is positive, that means DAC SAR is less than value. Then we increment SAR. Else we decrement as. So just check this function out. Okay. So the error is calculated as how far are we? Okay. So maybe this is a big error. Whereas when you come very close, okay, suppose the SAR is 98, and then the output will be 3 point. This is the value that the DAC will provide, and the value that you may have provided may be 3.81 or something like. So then the difference is very small. It's less than what. So then it will stop. Otherwise, it will keep going. So let us first see whether this works. Now we have to try and convert. Okay, and this can be a task, I think. So it will leave behind the converted value in task. So we can try converting some arbitrary value, like example ADC dot convert. Let us say 3.82 volts, and then we'll display SAR equals percentage D. So we are trying one possible value. Should be example ADC. Right? If error is less than or equal to accuracy, so let us make sure that we are printing it out correctly. The absolute function has not worked. Absolute value. We have to write so this. The value is 3.82. The error is accuracy is not correctly calculated. We have declared max and min as real. So let's see how this works. Okay. So there are some gotchas here. Okay. It's just like C language. The first error was, see, I had to put this in parenthesis because, see, if I write define apps x equal to x greater than 0, then x else minus x. This is how I have written. Okay. Now, when I call it, if I write apps x1 minus x2, right? So unfortunately, it will do it exactly like this. It will say x1 minus x2 greater than 0, right? Then x1 minus x2 else minus of x1 minus x2. See, it will do something like this. Okay. And this won't evaluate correctly. So parentheses will be required. Okay. So that was the first error. And the second error, I think, was this accuracy was not getting calculated correctly. I still don't know why the other didn't work. So max minus min divided by works. Okay, this is a real number, and that divided by integer is seems to be okay, right? Oh, there are some gotchas like that. Okay, so it has found 97 as the value. Okay. Similarly, let us try um, minus 4 point. So this time it should give you something like minus 107. So remember that the least value is minus 127. Okay. So if you try minus 5 or something like that, then it should give you minus Possibly it will give you minus 127. So it didn't quite give you minus 128. And the SAR ADC actually only the first 8 bits are valuable. The remaining are like we have made room for it may look odd that we are actually printing all the bits. So maybe we should print only the 8 bits. Right? So we can try to make it all clean it up. So define ADC bits or something like that. So let us say we call it 8. Max volt is 5.0. Min volts is minus 5.0. So that we can pass it. So this is a maximum voltage, this is a minimum voltage. Then we are converting some random values. Okay, we can write a loop and try to convert all the values, right? But I think it is okay. What you can try to do is like, you can try to improve this algorithm. You shouldn't have to go one at a time, right? See, for example, if I'm searching for, there are many names in the directory, right? I want to look for Ravi Kumar. So I open at some random page, and if I find, let us say, the name there is, let us say, Santosh, then I have gone too far. So between the A and S, I had to go somewhere in between. So you can use the technique to search faster. Right now, it is going very slow. In the worst case, it may take like 128 clocks. We have not put a clock here, but basically every call to convert is like this every iteration of this loop is like one clock. So is that clear? How the ADC works? Is this example clear to everybody? Is there anything that you want to explain? So if you have that, if you remember, we had written a uh, counter. See, the DAC is somewhat very straightforward. It was very simple for us, right? Mm. We can try taking a sinusoidal waveform and taking each of these values and sample it at regular intervals of time, and then giving it to your ADC and calculating the values. And then you will have one module called sign generator, which will keep on giving these values, intermediate values, and then that will go to an ADC, and that will give me the digital values. And if you want, we can even put a DAC here. and see how the new waveform looks like. Will it be how closely it resembles the original wave? So instead of converting random signals, here I have just took some random value, -5, etc. But you could write a loop here. Okay, so I will leave this as an exercise. Generate values of some sinusoidal waveform. So say you cannot exceed 5 volts. That's the only thing, right? If you exceed 5 volts, the ADC will not work correctly, right? Let us say you have taken 3.2 sine 2 pi ft or something like that. For different values of t. And then pass this to the ADC. Take f to be some value. F is, let us say, 50 hertz or something. And then drive the ADC. Then reconstruct the waveform with an ADC, maybe DAC, and check if your how much error has been committed by the ADC. The ADC will make some error, okay, because there is a limitation. We cannot have more than certain number of bits, right? And you can see how much if I increase it from 8 bits to 16 bits, I may get a better waveform. So you can make it into a small mini project by bringing in MATLAB. Okay. So plotting, I don't think is supported in your system Verilog. System Verilog can, I think it can plot these waveforms like this EP waveform which I showed you, but analog waveforms and all it won't be able to plot. So you have to dump this data into some file and then load that into MATLAB and then plot it there or any other. It doesn't have to be MATLAB. It could be any other software that can be used to plot. So this is the kind of thing that you will end up doing when you are, see you have to maybe include analog waveforms in your study because that is important. Maybe there is a sensor which brings analog values. Okay, so the sensor values may be in some Excel sheet, right? And that has to be imported into this test bench, and then that has to be converted, right? And then that depending on the sensor value, you may be taking some action, right? So all that can be done, right? So you can either or alternately bring in the values from an Excel sheet. So you should become adjusted to or rather accustomed to doing such things. Okay, so try that as a small mini project. That clear to everybody what I am asking for you to do. So Professor Vineet Sahula, if they do any of the projects that we are recommending, you can give them some sort of letter of recommendation other than the certificate, saying they excelled in whatever they were doing. All right. So let me send this out to you. So this will be so we looked at a little bit of mixed signal. Okay, we can't do too much, but we have done a little bit. So yesterday we did some analog stuff. Today we did some mixed signal and stuff like that. See, the class can be used to do many of those things. Okay, it doesn't matter, right? I mean, whatever that. Um, the other thing I wanted to do is make that binary search. Okay, I forgot to tell you. So the exercise I am assigning to you, right, is modify the ADC to do binary search. Okay. Even in binary search, I think there are some interesting ways they can do. I think there is a Fibonacci search and so many things are there. So any simple binary search is also okay. And also use this, take an Excel sheet where you put analog values in the range. See, there are so many variations. See, the analog values may not be in the range that we want. Then you may have to do some scaling and all that stuff, right? So that is where you have to, you know, apply the knowledge that you have gained. What else? Somebody has put some chat. Sir, please repeat. There was internet issues. Okay. What do you want me to the exercise? Is that what you want me to repeat? Okay. Exercise. Modify the ADC to perform binary search instead of linear code. Okay, that is the first thing. And then read read the analog values from an Excel sheet. Okay, and apply the conversion and obtain the digital values. Okay. So the sensor values, assuming that the Excel sheet contains data from some sort of a sensor, temperature sensor or whatever, right? And you can also try convert the values back. You can also try generate a sinusoidal wave using dollar sign built-in function and convert it to digital. Convert the digital waveform back to display. You can analyze the created wave for noise. Okay. The noise is introduced by your digitization. So I can put this in your chat. Is it clear to everybody? Anything that is not clear? Also, brief what you have taken before means you missed everything. If you miss everything, it is difficult to repeat. Yes. So what I recommend is one of the participants can maybe help you, and they can explain what I explained. So I just created a simple model for analog to digital conversion. Is okay? Professor Poonam Kadam, anything that you missed? How much did you miss? Okay. Sorry about that. I think looks like you have had some internet problems. Any questions? Any questions? Okay, good. So there are a couple of things that we have, you know, maybe it's worth mentioning, right? See, one is called property. Okay, property checks. So maybe we should go to 437 or something like that. So this very long, this system very long, they have developed a way to for verification engineers to write what are called as properties. See, we have seen assertions already, right? I think we talked about assertions in an earlier class. Right? What is an assertion? It is a we expect some property to be true. Say, for example, if you have written a model for the let us say some sort of an encoder or a decoder, whatever. Let us take a decoder. Right? Suppose we have suppose we have developed some sort of a decoder. A very simple decoder is let us say 3 to 8 decoder. So a property that the decoder must satisfy is that only one of the outputs must be one. If there is any bug in the design of the decoder, then more than one output may be. So that is a violation. Okay, we should not have that situation. Similarly, I don't know whether I can have a property for ADC. Okay, there is an ADC. It has converted this analog value x into some digital value y. So the if you convert this guy back to analog, so x and x prime, the difference if you take, okay, and then take the yeah, absolute value, then it should be less than some one bit error. So this should be the property. Otherwise, the ADC is not doing right. So we could write properties of this nature uh, to verify whether the design is has any bugs, right? So the assert statement somewhat looks like this. Assert whatever that you think should be true. Okay. So for example, you may want to write an assertion that exactly one of these must be one. Okay. I think there is one dollars count or something like that is there. Okay, dollar count. I've forgotten this. We suppose this output of the decode is called decoder out. Dollar count will return the number of ones. And if this is not equal to 1, we are okay. I don't know what it is called. We can just quickly check. Can anybody check what dollar count is? I mean, I don't remember this. But I have not told you these things, and for some strange reason, they are not documented in the system very long. So, for example, none of these are there, like dollar count. No system tasks are ever written here. See, these are all built in dollar min, dollar sum, dollar sign, etc. But this system Verilog manual did not document any of that stuff. So, can anybody check and tell me in the internet and what is that called? So then we can quickly develop a a assertion for decode. What is it called? Yeah, what is the dollar? What is the system task called? Is it dollar count? So suppose we have a module called decoder, dollar count ones. Okay. So dollar count ones is already available. Like that, count zeros may also be there, right? So let us say we take a three input. So suppose we have an input called in and output 7:0. And suppose we have gone ahead and assigned out 0 in 0 and in 1 and in. So this is our, if all the zeros, if all the inputs are zeros, we get 1 by inverting all of them. So in that way, we can write a number of these. So I may have made some mistakes. Okay, let us figure it out. So we have some decoder, and we can write a decoder test. So we'll instantiate decoder. We'll assign a we'll call it as in and 7-bit output product. This also takes the in and out. So we can try writing a exhaustive test, right? So assign into I, wait for 1 unit of time, and then assert that dollar count once or something like that of out. I don't know how to use this. It must be equal to 1. Okay, else dollar display there is some error. Or you could also, I think there is a dollar error also. You can give an error. So we did not get. So let us purposefully create one error. It gave an error. So when it was converting this, we should probably only display the laptop. So in decoding 001, 001 is also wrong. 001 seems alright to me. 011. Zero 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 one.
ಹೋಗಿ ಆಗತ್ತೆ ಅದ್ ಜಾಸ್ತಿ ಹೊತ್ತಿರೋ 2 ನಿಮಿಷ ಅದನ್ನ ಬ್ಯಾಟ್ರಿ ರೀಪ್ಲೇಸ್ ಮಾಡಿಸ್ಬೇಕು. ಅದನ್ನ ನೋಡಿದೆ ಅದು ಭಾರಿ ಕಾಂಪ್ಲಿಕೇಟೆಡ್ ವ್ಯವಹಾರ ಆಯ್ತು. ಯಾವ್ದು ಅದು ಬಿಚ್ಚಕ್ ಬರಲ್ಲ, ಅದು ಹಿಂಗ್ ಸೀಲ್ ಆಗಿರ್ತಾವೆ. ಅವೆಲ್ಲ ಅದೇ ಸೀಲ್ ಇದೆ.
Please mute yourself.
ತೋರಿಸಿರೋ ಒಂದು ಮಾಡ್ತಾರೆ, ಅದು ಸರ್ವಿಸ್ ಸೆಂಟರ್ನಾಗ ಮಾಡಿಸ್ಬೇಕಷ್ಟೇ. ಬ್ಯಾಟ್ರಿ ರಿಪ್ಲೇಸ್ ಮಾಡಿಸ್ಬೇಕು.
I request participant to mute themselves.
ಬೈಕ್ ಏನ್ ಮಾಡೋಣ ಈಗ? ಆಯ್ತಲ್ಲ, ಅದು ಅಲ್ಲಿ 2 ನಿಮಿಷ ಅದು. 1 ಪಾಯಿಂಟ್ ಇದು ಮಾಡ್ತಿದ್ದ.
Madam Nirmala, please mute yourself.
ಅವು ಟೈರ್ ಈ 2 ಬ್ಲೋ ಇಲ್ಲ ಈಗ. ಅವು ಯಾಕೆ ಹಾಗಾದ್ರೆ ಗಾಡಿನ ಇರಲ್ಲ.
Madam Nirmala, please mute yourself.
ಈಗ ತಗೊಂಬ ಸಾಯಂಕಾಲ.
Geeta,
ಹಾಕ್ಸ್ಬೇಕು.
Geeta,
ತಗೊಂಡು ಹೋಗ್ತೇನೆ. ಇಲ್ಲ
please mute Nirmala.
ನಿಮ್ಮ ಅಣ್ಣ ಬಂದ್ರೆ
What is the error?
ಏನಂತ ಏನು ಜಾಬ್ ಸಿಗ್ತಾ ಇಲ್ಲ. ಇಲ್ಲ ಅವನೇನಂದ ಯಾವಾಗ ಏನಂದ ಅಂದ್ರೆ
Sir, the indices in the design are in reverse order.
ಇರ್ತೀನಿ ಅಂತ ದುಡ್ಡು ಕಳ್ಸಕ್ ಆಗಲ್ಲ ಹುಡುಕು ಅಂತಂದ್ರೆ ಸಿಗ್ತಾ ಇಲ್ಲ ಅಂದ. ಬಂದು ಮನೆಯಾಗ ಇರ್ತೇನೆ ಅಂತ ಬಾರಪ್ಪ ಅಂತೇಳಿ.
Any idea why 1 is failing? 2 is 3 is also failing. What is error in my logic?
So the indices instead of 0, it is 2, and instead of 2, it is
Oh,
1.
this should be 210. Yeah, this should
Yes.
be right.
ನೇಹಾಂದ್ ಎಂಗೇಜ್ಮೆಂಟ್ ಐತೆ ಬೆಂಗಳೂರಲ್ಲಿ. ಎಲ್ಲ ಭಾನುವಾರ ಆಯ್ತು. 17ನೇ ತಾರೀಕು. ನಾವು ಬರ್ತೇವೆ ಬಾ ಅಲ್ಲಿ. ಎಲ್ಲಿ ಅಂತ ಗೊತ್ತಿಲ್ಲ ಅಲ್ಲಿ. ಲೊಕೇಶನ್ ಗೊತ್ತಿಲ್ಲ. ಮದುವೆ ಅಂತ ಕ್ಯೂಬಿಕ್ ಹೋಟ್ಲ. ಇದು 27 ಆಯ್ತು 7.
So now the error is actually at 4. That is where I made an error. Okay, this should be 100. Okay, but I made it into 110. Okay? So it is finding an error there, and also maybe at 110. 110 is 6 seems alright to me. Yeah, that could happen. See, when you put 110 in my current logic, what is going to happen is 110 will also generate, and 100 will also generate. So that is actually correct. See, here 2 things are getting selected, and here nobody is getting selected. So it's actually correct. Okay. So that is what I meant by assertions. So they have provided some such functions like count ones to make your life easier. Okay. Any doubts here? Everybody understood this exercise? So we built a simple decoder and introduced a bug here. And when you test it out, the assertions fail. So this display is not required. You need not display. Because in a bigger circuit, display may be not the best way of debugging. Okay, we just want to know if there is an assertion which is failed. Okay. Is that clear to everybody? I'll send this also to you. If anybody didn't understand, please ask. So this was an example of assertions. In addition to these kind of assertions, I think these are called simple assertions or something like that. Okay. So immediate assertions. This is an immediate assertion. And there are also concurrent assumptions, concurrent assertions, which is a lot more difficult, right? You can check for some properties in the data. Okay. See, for example, you can check if a particular signal goes high after another signal was asserted and things like that. Okay. So it is Verilog gives you a great deal of flexibility on defining sequences and this writing assertions on sequences and so on. Okay. So let me quickly show you one or two of these and so here is an example. So you can define a sort of a time sequence or something like that and say SXY refers to a sequence. If X were to become high 1 unit of time later, Y should also become high. So suppose you test this every clock cycle, then this sequence, this is telling you that if X were to become high, then Y will become high 1 unit of time later. You can also say it will become between 1 and 2. So if you write 1:2 in bracket like this, then that means Y may become high after 1 or 2 clock cycles. Okay. And there are many more complex ones like this. Okay. There is a great deal of detail in all these properties. Okay, you can see how complex the checking of properties is. Okay, so they have also given it only in the appendix. They have not bothered to explain all this in the main manual. Okay. So we can try one or two of these. Okay, but first you take lunch break and then come back. So we'll take a break. So Professor Sahula, is that okay?
Yes, sir.
I think they are nearing lunch, so maybe we
Yes,
can.
sir.
So now it is 1:42, so around 2:45.
Right, sir. Well,
Let me quickly look at the chats that were coming up and see whether there is anything I missed. System Verilog material I have given, no? See, Pinky, System Verilog, there are two books that you can refer to. One is a System Verilog primer, which is Indian edition is available. J. Bhaskar. I have sent it earlier, right? So that is one thing. Then the manual is easy to download. I have given you the link, right? Just Google for System Verilog manual. Then the other book is by Chris Peer. That is also available if you wish to buy. Okay. So you can, these are the three sources that you can look at. Okay. The book by J. Bhaskar, the book by Chris Peer, and the manual itself. So manual is good for quick reference. Okay. But if you want to get maybe some more explanation, etc., you may find it in that. Bhaskar is very affordable. It may not be more than, I think when I bought it, it was 500 rupees or something. So that is what I have with me. I also have Crispier's book, but it's a bit expensive. All right. Anything else? All right. We'll take a break and come back in 1 hour.